Thank you. And so thank you very much for the invitation. So the work I will be talking about is a joint work with Simeng Wang, who is now in Harbin in China. And so, well, the starting point of the story of Pointwise Ergodic theorem is the famous theorem of Birkhoff, so which tells you that if you take a measure preserving transformation of a measure space and so you consider the associated ergodic averages, meaning that you take a function f in an LP of omega, and so you move around the function f by the transformation n times, you average that. And so these averages are going to converge almost everywhere to a t-invariant function. And so in this talk, I'm going to be interested in, well, basically generalizing this theorem. In the case where, so in the non-commutative case, instead of having transformation of a classical measure space, you're going to have a transformation of a fine Neumann algebra equipped with a trace. And instead of having only one transformation acting on this fine Neumann algebra, you're going to have a group of transformation. And I'm going to focus on the case of having an amenable group acting on M. So there are things that have been done and that are possible outside of this case, but these are some kind of very distinct pictures. So I'm going to focus on the case of an action of an amenable group. So, well, a bit of definitions to make all that precise. So there is going to be the algebra with the trace, the amenable group and so the action this time is going to be by, so I forgot one condition, trace preserving star automorphisms. So to generalize this transformation of the measure space. And the ergodic averages, so you also have to give meaning to that. So it's the same idea. So you take instead, so now you don't have functions but operators x. You move it around by the action of g on fixed sets, so the fn's, and you average it. Okay, and so this gives you ergodic averages. So for the action of only one operator, you had a very natural sequence fn to take. It was just integers from 0 to n. But there in a general group, you have to make some choices. And so this is going to have to be determined. So the question, very generally, is can we find such a sequence, fn, so of compact set of the group that is going to exhaust the group in some way, such that if you consider the ergodic averages, they are going to converge pointwise to a G-invariant operator. Okay, and so this has to give you a bit of idea of the timeline of this question on the non-commutative side. So the first kind of Birkhoff type theorem in the non-commutative context were studied by Lenz, and so it's for a single transformation on a fundamental algebra. So there is no mention of x in LP. But this already began a first series of papers. So there are some generalizations by Kummerer, and so in particular the work of Konz and Dong and Gok is already for actions of amenable groups. So they generalize to the non-commutative context what was known at the time, which was not the general theorem. and some work that is going to be more in the spirit of what I'm going to talk about today, in the threshold case by Jeden. And so there he studies the case of operators in L1 of M. Okay, and so later, after some change of perspectives and development in non-commutative harmonic analysis, Junge and Xu gave a kind of complete non-commutative analog of Birkhoff's ergodic theorem. So this time you really consider X in LP of M and still a single transformation. And so it's starting from this time that the question of generalizing that to actions of amenable groups became open. And so not kind of recently, this was studied already in depth by Hong, Liao, and Wang. And so they obtained the satisfying result for G of polynomial growth. So we'll see later what was missing at the time. And so a kind of almost independently to that, there was development in the commutative side for this kind of ergodic theorem, but for actions of amenable groups on classical measure spaces. And well, so this question before here was completely answered by the positive by Lindenstrauss in 2001 if M is commutative. Okay, so some precisions about, because for now there are some elements in the questions that maybe need a bit of definition. So if you start with a Fundamental algebra and equipped with a trace, then there is a very natural way to define non-commutative LP spaces. So you consider the trace as a generalization, let's say a non-commutative analog of an integral. And in this case, there is really one formula that is natural. So it's to take the trace of the modulus of x to the power p and take that to the power 1 over p. So it happens to give a norm. So when you complete when you take completion of the elements for which this norm is finite in M, you get a Banach space, and this family of Banach spaces has really nice properties mimicking the ones of classical LP spaces. You have so one important thing, you have a bigger space of L0 of M, which is going to correspond to the space of measurable functions. So these are possibly unbounded operators. And, well, so I guess this is not only when you are interested in non-commutative LP spaces, but it's good to, I remind that it's good to think about projections in M as, well, the non-commutative equivalent of sets. So they are to be sort of as characteristic functions. So these are a nice family of spaces. And another thing that was in the question is a pointwise convergence. So of course, in this non-commutative context, we don't have points anymore. So we have to formulate pointwise convergence in a functional way. And so this was done by Lenz. So fortunately, there is a way in the classical setting to formulate pointwise convergence completely functionally, and well, this is these quantifications. So instead of saying that at every point there is convergence, what you say is that for every epsilon that you can fix, there is a projection that is epsilon close to 1, so it covers almost all of the space. And on this projection, your sequence, I don't know why I put 0, so x is 0 there. Your sequence converges converges in uniform norm. So it's a uniform convergence, but in an arbitrary large set that do not cover the whole space. And so in this non-commutative, to quantify that for operators, there is a bit of ambiguity when you say that the sequence xn converges on the projection, so you can multiply on the left, on the right, on both sides, which gives rise to two definitions. So one when you multiply on one side, and one when you multiply on both sides. Okay, so when M is commutative and finite, this is completely equivalent to pointwise convergence. This is Birkhoff's theorem. When M is commutative and not finite, the almost uniform convergence is stronger. Well, it's not a harmless definition. Some things that you would want to write become actually false. But well, it generalizes well, at least the notion of pointwise convergence. So this is the one that has been used since Lenz introduced it. Okay, so now I recall the question. So we want to find this sequence of compact set of our group. We have ergodic averages associated to those compact sets, and so we want it to converge those ergodic averages when they are applied to a function in LP. So now we know what LP is, and we want to converge almost uniformly or bilaterally almost uniformly. We know what kind of convergence we want. Okay, and so we know that there is a kind of so because of this large literature, we know basically which steps to follow. And so in short, there are kind of two ingredients. The first ingredient is to prove that there is this convergence in a dense subset of LP of M by kind of more brute force method. And for this, the crucial ingredient is, in the case of amenable groups, is going to be to prove the asymptotic invariance of these ergodic averages by the action of the group G. And in fact, this asymptotic invariance is well, when you take a G, an amenable group, you can obtain it very simply by imposing that the sequence Fn is a Follner sequence. Because, well, if you remember a little bit what is the ergodic average, the ergodic average here is the integral over Fn. And so inside of this P norm here, okay, you get here an integral over Fn, and here an integral over Gfn, and it's exactly the definition of a Follner sequence to say that basically Gfn and Fn are going to be very close, and so this here is going to cancel out almost everything is going to cancel out, and is going to go to zero when n goes to infinity. So well, if you don't know what the Follner sequence is, it's exactly what you need to put here so that this is asymptotically invariant. So these are asymptotically invariant sets in the group. Okay, and so this is basically for free in amenable groups. And the second ingredient that is not for free is maximal inequality. So in general, this would be for a classical. In the classical case, you want to prove something like that, so that you can control the supremum of this family of ergodic averages in LP norm if X is if you start with an LP function. And this is going to be again related to the geometry of amenable groups, but in a more difficult way. And so there is kind of a third ingredient, which would be to manage to link the two to obtain convergence. But this is also okay. So really, what needs to be understood is this maximal inequality. And well, the first thing is that if you take operators instead of functions, you cannot define the supremum. So you have to invent some ways to formulate maximal inequalities even without supremum. So this was already done by Lenz in an even more general kind of formulation, but with developments in non-commutative harmonic analysis, and so definition given by Pizier and extended and used after by Junge. So we have actually, so we don't have a supremum because, well, it cannot be defined, but you have an analog. So this is really here just a notation. There is not really an element inside here. It's a notation for what would be the LP norm of the supremum of the xn's. And so, well, for general sequences xn, this is given by taking this infimum of this norm over all possible factorizations of the sequence xn. But it becomes very intuitive with this second definition. So if you take a sequence of positive operators, then the norm of the supremum is just the infimum of all the LP norms of operators that majorize the whole sequence. So this second definition, I think, is very intuitive. So this, if you construct binary spaces if you construct spaces using these norms, you get a binary space for p bigger than 1, not 0. Okay, so for in L infinity is just bounded sequences, but this time these have some pathological behavior. So maybe this example not closed by taking not closed by taking absolute value, of course, is not intuitive because you could do that in a commutative case, but it's actually when you think about it, it's actually pretty logical that this should not be true in the non-commutative case. But there are some other properties which are quite bad of those spaces, so they are not that easy to manipulate. And we'll need another kind of formulation for maximal inequalities, and this is because in the particular case of L1, even in the classical theory, you cannot have a good maximal inequality of this kind here. Here you have to put a weak L1 space. So, okay. So basically, a weak type inequality, it's weaker than what was if we could control the supremum. But what we can control is the level sets of the supremum. So here I wrote it for a general operator T. You can imagine T to be the supremum of the family of ergodic averages. And so we say that it is of weak type 1,1 if, so for any lambda strictly bigger than 0, we can control the size of the level set, so when TF is bigger than lambda, by, well, exactly what we would expect. So this is, so you multiply here by lambda, and here you have an absolute constant and the norm of F1. So by Markov's inequality, this is exactly the control that you would get if you had this, except that you don't have this, you just have the control of the level sets. And in the non-commutative case, so there is there are several possibilities for generalizing this, but the one that actually works that can be proved in the theory is this one. So if you have a sequence of maps, you say that it is of weak type 1,1. If so, you want to control the level set, so you want to be able to find a projection E, which is going to play the role of where the Sn of x are all less than lambda. So E is where all of the Sn of x is less than lambda, and you want the complement of E, so 1 minus E, to have the same kind of control that was there. So lambda tau of 1 minus e is less than, is controlled by the norm of x in L1. Okay. And so this is exactly the kind of inequality that happened in the non-commutative case, and this was already the paper of Jeden actually uses this kind of weak type inequality to deduce bilateral almost uniform convergence of ergodic averages. And so, well, okay, with all this formulation, our goal is kind of reduced to this new question. So we want to find a sequence in our group G. We want it to be a Fourier sequence to have this asymptotic invariance, and we want the ergodic averages to satisfy a weak type 1-1 inequality, which I developed later. And so there are some things that I have not said to show that this is enough. So yeah, this one I have said. And the second is that by an interpolation theorem of Junger and Xu, the weak type inequality in L1 is actually enough because you can get the LP case by well, this kind of principle. So interpolation. Interpolation just means that, so if you have inequalities at endpoints of this LP family, then you get inequalities for the values of P in between. And this is exactly what, yeah, this is still true for these non-commutative maximal norms. Okay, so the problem is reduced to that, and there is a last reduction, which is that actually we are going to be able to consider only one action, because of transference principles. So there is kind of a canonical action of group G, which is the action of G on L infinity of G by translations. And well, you can extend it to act on operator valued functions, but still, so it's just a tensor product of this action. And this actually happens to be an action that controls every other action on non-commutative spaces by the group G. So this is exactly what the transference theorem says. So if the sequence of ergodic averages associated to this particular action is of weak type 1-1, then it is for any other action it is also of weak type 1-1. And so now we only need to consider this action. And so this is yeah. So in the case where you remove the M is just C. This is the maximal inequality that was proved by Lindenstrauss. But so here the kind of bad news is that we really don't know how to use similar techniques, even in simpler cases than this. In the simplest maximal inequalities, we don't know how to use the classical techniques which are covering lemmas. But still, this is a very good reduction for us because well, when you get to this semi-commutative setting, so really the action is only in the commutative part, and well, you have operator valued functions rather than just operators. You're going to be able to use at least some techniques and inspirations from classical analysis. Okay. So now I will explain a little bit how to avoid this use of covering lemmas, and well, yeah, how this kind of maximal inequalities are proved in this non-commutative setting. And so this is often by using martingale theory. So actually, maybe one remark here is that Jeden's maximal inequality does not use martingale theory. It's really just a very, I guess, unique proof. As far as I know, it's just one argument that works in the specific case of one transformation. And in this sense, it's different from a lot of other maximal inequalities that are proved by reducing to martingale theory, or actually by duality. But okay. So what happens for a martingale? So the martingale theory has a very natural generalization to non-commutative measure theory. So you take a family, a nested family of subalgebra of subalgebras of your start of the algebra M that you started with, and so if you take all those subalgebras to be semi-finite, you have conditional expectations onto those algebras, and this enables you to define martingale, so which would be the sequence En of x for an x in LP. And for those conditional expectations, you have maximal inequalities. So this was well known in this is called Dub's maximal inequality in the commutative context, and this was generalized to non-commutative martingales by Junge. And so here I have used actually another notation, but this is again the supremum of the En of x, the virtual supremum of the En of x is dominated by so in LP is dominated by the norm of x in LP. And actually in the 70s, Cuculescu had already proved the weak type in the corresponding weak type 1-1 inequality. So this we know in full generality. For really any sequence, nested sequence of subalgebras. And so we are going to try and use that to obtain something on ergodic averages. So we are actually going to have to use only a very specific form of martingales, so which are in this semi-commutative case. So there is a way to construct subalgebras of n, which is just taking, for now, just take one partition of omega. So the elements of the partition, I'm going to call them atoms. And if you assume that every atom is finite, then you can consider the algebra of functions which are constant in every atom. And so the conditional expectation onto this algebra is really a kind of an averaging operator. So you average over so if you have a point in an atom, then it's the value of the conditional expectation of a function f at that point is the average of f on this atom. So this is what is written here. And well, to have a nested family of such algebras, you just need to start with a nested family of partitions. So yeah, partitions which become I guess in this case it's going to be less and less fine. Yeah, so yeah, less and less fine. And the classical example of that is used very often of such a martingale is the dyadic martingale, where you decompose RD by cutting it into cubes, and so you cut it into cubes of let's say size 1 and of edge 1, and in one direction you divide the cube by 2 at every generation to get smaller and smaller atoms, and in the other you take only cubes that are twice bigger to get generations of bigger cubes. So okay. And so this, with this dyadic martingale, you can already prove a quite important maximal inequality that is of the form of this maximal inequality for ergodic averages. So in the particular case of the group being the reals, and the averaging sets being the interval minus 2 to the power n, 2 to the power n, then you get as ergodic averages, so averages of the function on intervals centered at the point, and so okay, and so this by a trick invented by May, you can actually dominate pointwise these ergodic averages by the martingale the conditional expectations if you take two different grids, if you take two different two different filtrations, basically. Okay, and so this implies directly that you have, since you have a maximal inequality for those elements here, and you can dominate every one of those elements by them, but then you can transfer maximal inequality and also weak type maximal inequality from this general martingale one to in this particular case of ergodic averages. And so how does that work? So the first observation is very simple. If you average in a ball that sits inside of a cube, and the ball is not much smaller than the cube, then of course the average on the ball is going to be, here you have F positive, the average on the ball is going to be dominated by the average of the cube. But the problem, of course, is that when you have a fixed grid and you have balls that can be centered at every point, you might be in the case where the ball intersects the border of cubes, and then you cannot control the average of the ball by any of the value of the conditional expectations. And so the idea of May is, instead of using just one grid with this observation, to use multiple grids. So in dimension 1 you can use only 2, but to draw it, I drew it in dimension 2. You have to use 3 different ones. And so here you can notice that using 3 grids, so they are shifted in both directions by a factor 1/3. And so if you take a ball that is of diameter less than 1/3, then you can't make it intersect the 3 grids. So here I drew it, it intersects the violet and the yellow one, then it cannot intersect the black one. And so, well, in this particular case, the average over this ball is going to be dominated by the average over this cube. And in any point, pointwise, you're going to have domination by one of the 3 ergodic averages. Okay, so this is a very simple geometric idea, but actually it can be replicated in a large class of spaces. So this is a geometric theorem, so construction by Itonen and Kairema, that tells you that actually in any doubling space, meaning, so doubling means that there is this factor beta that tells you that any ball that you take in the space, then you can consider the ball and beta times the ball, which is the dilation of the ball by a factor beta. Then beta times the ball can be covered by a finite number of, so control finite number of balls of radius, the radius of this starting ball here. So yeah, okay. So this is one condition that that tells you that your space behaves in a small part like Euclidean spaces. And so in the case of a doubling metric space, then you can, so this theorem tells you that you can replicate the idea of May. You can control, you can find a finite number of filtrations such that any ball in the space is dominated by one of the atoms of one of the partitions. And so this means that so groups of polynomial growth seen as metric spaces are going to be doubling, and so this means that you can obtain a maximal inequality in the case of groups of polynomial growth. And outside of that, this lemma I'm pretty sure it cannot work. For example, for Lamplighter groups, you cannot find such finite number of partitions. Okay. I had maybe. Okay. And so maybe one remark is that this maximal inequality actually has, and the theorem obtained has actually can be formulated completely outside of group theory, because so when you have that, then the Follner sequence that you're going to take are balls of radius n in the group, and so actually the whole theorem can be formulated in terms of a doubling metric space and taking averages over balls that are bigger and bigger. So really, this is just a metric. This is a metric theorem that, in particular, applies to groups of polynomial growth. Okay, so in the rest, it's going to be the group structure is going to be more apparent. Okay, so there is a second way that is actually an older way to compare martingale and to link martingale and ergodic theory, which was used a lot by Bourgain. And so the idea is to form this sequence of differences. So you have, you have here your conditional expectations, and here your averages, and you just form the sequence of the difference, and you hope to control it in some way, but this time, in some quantitative way, not just qualitatively pointwise. So the idea was used to transfer properties like variational inequalities that could be proved for martingales but could not be proved in the case of ergodic theory. So to transfer those, and also to obtain dimension-free estimates for certain maximal inequality for averages, because in martingale theory you have an absolute constant that works for any martingale when doing this maximal inequality, and so the goal was to transfer that to work on the constants on certain maximal inequalities. Okay, and so well, the idea can also be used there. So you form this difference operator, and the norm that you put on this sequence this time is not a supremum. It's it's z here, a square function operator. So which again this the expression makes sense in the non-commutative for Dn operators, but I'm not going to give the details, but for operators you have to use another expression, but it's to be thought of as a square function. And so Hong and Xu, they extended the fact that the boundedness of this difference operator to operator valued function in this the case that I was talking about earlier. So Fn being balls in these times in Rd, and Pn being the dyadic filtration. And so here, so you have this norm that I have not defined. But what is important is that you have this kind of weak type control, and the weak type control of the difference is going to enable to use the maximal inequality for martingales and to transfer it to ergodic averages. And what is important for us, so we are looking for basically a proof that doesn't use geometric ideas which are as strong as the one before. So the one before was really to have the balls, so the Fourier sets and the atoms of the filtrations really had to have similar shapes. And well, there maybe it uses less. And so well, one first geometric advantage is that it uses only one martingale. And so, yeah, so this is basically where our work started. And we want, because, so, yeah, the observation is that in some groups that are not of polynomial growth, you have one, at least one filtration that is very natural. So, for example, for Lamplighter groups. And so, yeah, the idea was to try and understand if the ideas of these, yeah, that enable to control this difference here can go over to more general setting. And it is the case. And it is the case because actually here what is important is some invariance property of atoms with respect to the Fourier sets and also in the other direction. So the reason why the operator, the difference operator D is bounded is because at every generation the operator dk, so the difference between ergodic average and conditional expectation has a very precise local behavior. So if a function f is localized in a certain sense, then the operator dk is going to become very small. So here here is one example. So if f is so if the average of f in every cube of the generation n is 0, then when you apply dk for k much bigger than n, the operator dk is going to become very small. And so, okay, so this is the first, this is some geometric observations, and then to finish the proof, you have to actually be able to decompose any function f into some small parts which are all localized in both ways. And so, well, this is done. So this was some not recent development in non-commutative Calderon-Zygmunt theory that enables to do that. So you can actually do that, and you have all the good estimates to put it back together later. But okay, what I want more to explain is that so these local estimates come from very simple geometric observations. So if you have cubes that are very small, and you have this condition that the function f has mean 0 in every cube, and now you want to apply the difference operator for a generation that is that comes that comes a lot before. So you're going to have the difference between an average over some ball and an average over some big cube. So the average over the big cube by this is going to be 0. So actually the difference operator is only going to see this average over the big ball. And well, in the average over the big ball, since the average over all these little cubes here is 0, the only part that is going to be of importance when you compute the integral of the function f over the ball is the green part here. Okay, And this green part, since in one direction it has width 2 to the power minus k, you end up with this with this estimate. So the volume of the part that is of importance is the 2 to the power n minus k times the volume that you should have integrated on, and this is exactly where the 2 to the power n minus k comes here. Okay, so now in a general group, you want to replicate what happens here, and so the good news is that this border is exactly what you are able to control in an amenable group, because basically the border, the border tells you that when you the border being small is a way of saying that B is invariant by is very invariant by multiplication by the shape of the small cube. Okay, and so this is exactly what can happen and what always happen in amenable groups. You can always find a shapes that are very invariant with respect to a fixed one. And so, okay, so I explained a little bit the setup that we need. So we need, of course, a Fourier sequence. So this is going to be the balls in a general group. You need a filtration, so which is going to be thought of as the dyadic filtration, and you need this auxiliary sequence Bn, which is to be thought of as the shape of the atoms of the filtration. So in the case of the dyadic filtration, this is going to be a cube of size 2 to the power minus n, and then what you need is exactly what you ask for is exactly what you need to replicate this local estimate that I showed before. So you want a big balls to be very invariant with respect to multiplication by small atoms, and you want big atoms to be very invariant with respect to multiplication by big balls. And with this kind of conditions, then you can obtain you can bound this difference operator and follow then the whole chain of implications. So the boundedness of the difference operator implies the boundedness of the maximal operator, which implies the convergence of ergodic averages. And now, of course, you have to be able to construct such a filtration and such a sequence. And actually, we know that it's possible in every discrete amenable group. So, but a drawback of this method, if you just look at it with a scalar valued function, is that the sequence Fn that we obtain in spirit is given the construction that exists for this for this sequence Fn. They are much more lacunary than the one obtained by Lindenstrauss. But on the other way, the information that we have with the maximal with the difference operators is actually stronger. So there are some. If we restrict to the classical case, there is some plus and minus compared to the theorem of Lindenstrauss. And so now I will finish by talking a little bit about what are these geometric conditions and these geometric constructions that we need to be able to do on amenable groups to construct those filtrations. And so if you condense condense it into one specific property, you want to be able to tile, so to obtain partitions of your group G, such that every atom of so you take one invariance condition, so one small delta and one compact in G, and you want to have every atom to be delta invariant by multiplication by K. So yeah, so you want your atoms to verify an arbitrary good invariance condition, and you want your remark that this can always be done very simply by taking atoms that are bigger and bigger using the Follner condition. But the reason why it becomes a bit tricky is that you want your atoms to be uniformly bounded. Basically, this would mean if you take a metric version of this condition, it would mean that they have bounded diameter. Okay, and a construction of Dovnarovich, Ušek, and Zhang tells us that every discrete amenable group admits such tilings. Okay, and so the origin actually of the construction of this kind of tilings is a work of Ornstein and Weiss in the 80s, which was actually very central for the development of ergodic theory of amenable groups. Okay, so this is the base construction, and what and we not need to use the full power of Dovnarovich, Ušek, and Zhang. They also have some conditions of entropy, and okay, but okay, so they add some ideas to this original construction of Ornstein and Weiss, and are able to prove to construct this kind of tilings. And beyond this discrete case, so so we don't know if we can find such tilings, but what we'll do basically the construction of Ornstein and Weiss, what it does is to give you not really a partition of your group G, but a partition of epsilon of 1 minus epsilon of the volume of G. So you have some holes, some holes inside of the group, and what we noticed. So you don't need to read the details here, but what we noticed is that even with some holes inside of our partitions, which so to continue to use the same language, it's good to just cover them by atoms, but atoms for which we don't have any good properties. The proof, then the analytic arguments that follow can still apply, just because basically you can. So the idea would be just to, so if you take one function f, then you can decompose it such that every one of the fi's is only inside of the cubes that you can control. So up to translation. Okay, so for every fi you can translate your grids such that fi is supported only in atoms for which atoms that have a good invariance condition, and so if fi is only supported in those atoms, you can do the geometric thing that I showed earlier, and the proof goes on. So. And so still using the same ideas of Ornstein and Weiss, and well, once again, there needs to be some adaptations, but still with the same base construction, we can show that every amenable group has this kind of filtered Fourier sequence, so this geometric setup, but with some bad atoms, but not too many. And this allows to, well, so here you don't have only one difference operator, but a kind of a family of difference operator, but this is enough to make the maximal inequality go over and conclude the convergence. So it's still so with these ideas, it's still possible to for any amenable group to find a Fourier sequence for which there is convergence of the ergodic averages in this almost uniform convergence sense. Okay, so I will stop here. Thank you.
Thank you very much. So are there questions or comments?
Yes. Okay, thank you for the very nice result. I just want to ask you the following, because it's clear that somehow if you take a subsequence of your sequence, it will still work.
Yeah.
So there is the question of evaluating how lacunary your actual sequence is, I presume. So is there a way to evaluate this and to say that you know, that it's sufficiently not so lacunary?
So actually, even in Lindenstrauss' paper, there is an open question, which is, can you take an exponentially growing sequence?
For instance, yes.
And I think it's still open, as far as I know, it's still open. But and so in spirit, in spirit, because it's very credible with how you construct his tempered Fourier sequence, that you can always find an exponentially growing one, because basically you construct it by induction, and the next Fourier set has to be invariant by the one before.
What you are saying is the following: is that it has to be at least exponential when the group is not polynomial growth. So I mean,
yes.
But the question is, can it be just that?
Yeah. So this is open, but in spirit, for his construction, it's very believable that it is true given how you construct it. But for our sequences.
Yes.
It's also by induction,
Yes.
but at every step you have to put some other Fourier set that you don't see.
It could be like exponential.
Yeah, exactly. So in spirit, R is exponential of exponential, and his is exponential, but this is only, in all the examples, actually, they are exponential. Examples that we know that are, but. So but in spirit, I think it would be very difficult to show that in any amenable group our sequence is exponential, and much more believable the ones of Lindenstrauss. Yeah.
Et par exemple, pour l'allumeur de réverbère, il y a une construction spécifique, là on sait exactement, on connaît le bonne suite.
Yes, oui. So it's actually what started our work. It's because Romain Teixeira and others have a paper where they construct some filtrations of the lamplighter, and they are exponential, and so Simeng actually thought that it could be used maybe to continue the work that he did, and so for the lamplighters it works very well.
Yes, I have another question, which is just a lack of knowledge. When you look at the two LP space and you do the Lyon's real interpolation between them, then you get spaces like L1 infinity, for instance. Is there a relation between this space and the type of weak L11?
Yes.
There is.
Yes. So in the case where you don't consider maximal function, then it is exactly a boundedness into this space. But actually, this is one of the bad things about these maximal norms. Real interpolation doesn't work anymore. So this is the bad thing.
Yes, because real interpolation then would give you a lot of other results, intermediate between the two. Isn't it?
Yes, yes, yes. And it would make, yeah.
It would make sense better. Okay.
Any other question or comment? Well, if not, let us thank Léonard again.